Okay. So we have the satellite set up on the roof, and Chris C., who's a main satellite guy at Blockstream, is up there with a phone camera and a Zoom call, so he's going to try and show us what's happening. And I think I will kick off by showing some of the equipment that you use to do this in close-up. And maybe we could show the Blockstream Satellite launch video from last year, if that could be presented on the laptop, perhaps. Yeah, we have audio for Chris, but the Zoom video should be presented from down here because of bandwidth. So I don't know if there's anybody at the laptop, though. Anyway, let's start with the equipment.
Camera on the table, please. Desk camera, thank you. The physical desk, thank you.
So I'll use this. Oh. So this device is a USB SDR. So these things, depending on the model, this is another brand. It's basically used for converting the analog signal from the satellite receiving dish into digital, and then the signal processing is done on the laptop. So it's part of the way that we're able to keep the equipment costs down, because these devices range in price from $10 to $15 on eBay or Alibaba to, $50 and the professional things that people do development on, a few $100s. Basically, we're not really using all of the features of it. It's just doing analog to digital conversion at this point. And the other thing you need to do is connect. So with the satellite dish, there are more parts. So this part of the satellite dish is the so-called LNB. It's a low noise block, and you'll see these at the end of satellite dish arms. So basically, we need a particular LNB to do this. It's not necessarily the standard one. It's used for other applications, so it's something you can buy readily. But it's a low noise one with less drift than usual, basically. So you connect this, like replace. If you're reusing an existing satellite dish, you replace it. So you unclamp it and put this one on, and then you need to get enough cable. I think I lost enough cables and down converters. So the main satellite connection is this larger cable, but there is also a finer cable like this one, and this is the type of connector that goes into the SDR equipment. So you'll have this kind of thing. And then the last thing is that the LNB is actually powered, but the power goes through the coax cable. So the power brick, that will stay inside the building, inside the house, and it sends power up to the satellite dish to power the LNB. Now, the other thing you have to do, and this is another brand, so there are many different brands. It's the software can support different SDRs. Now, the other thing you have to do is find the satellite dish, and this can be a little tricky, and that's what's been occupying us for the last few hours while we're hoping to demonstrate. So one thing you need is just a very simple piece of equipment, which is a compass, and there are smartphone applications. So there are smartphone applications which give you a crude picture of where the satellite is. So you just hold it up and it uses the smartphone's camera to find things. But there are more sophisticated things. This is a digital satellite finder. You can buy these for not too expensively. There are some simpler ones that just make a tone, so they beep when you get a higher signal. And when you've finished and you've found a satellite with it, you will unplug it and then switch to using the laptop. So in a little while, Chris will show you what that looks like once you get onto the software part of it. So I think I will pause there and we'll switch over to the laptop screen, and I think we should have audio from the laptop actually, so that Chris can show us what's happening.
Can you guys hear me? All right. Do you guys have a view from the roof? Yeah. Awesome. All right, so it's a gorgeous evening up here, and this is the Blockstream Satellite setup right here. As you can see, there's not much to it, just dish and a laptop. As Adam was mentioning earlier, this right here is the LNB, which basically the dish itself just collects the signal and focuses it to the LNB. And the LNB also down converts the frequency from like around 12 gigahertz down to about 1 gigahertz. So from there, we go through our spool of cable into a power supply, and that just powers the LNB right there. And then that connects back to the SDR interface, which is simply a analog digital converter in this case. It's taking the analog radio signal and converting it to digital, and all the actual decoding and demodulation is happening in software. And this right here is the Blockstream Satellite receiver. So as you can see, this signal right here, that is actually our signal. And oh, I just lost video, there we go. The constellation down here is BPSK modulation, so that kind of can give you an indication of signal strength. And this is basically what you see. Now there's a lot of other options to this for more advanced things. If you want to look at our frame synchronization, frequency synchronization, timing sync, etc. We don't need to get into all the details there. So once the data is processed by this, it gets simply output to a named pipe within the Linux system, and it's essentially a proprietary protocol that we came up with and is also open source that takes the Bitcoin blocks and routes them into a version of Bitcoin fiber designed for satellite. And if I switch over here, this right here is a log from Bitcoin fiber that's running. And as you can see, it's already been receiving block headers from the satellite. I'm a few little bit behind right now. So the satellite network actually rebroadcasts the last 144 blocks every approximately 3 to 4 hours. So if you miss the last 24 hours of blocks or missed any block in that period, it will catch back up. At the moment, you do need to start with a reasonably synchronized chain, because if you're more than 24 hours, it will not catch all the way up, but that's a feature we're looking to add in the near future as we increase the amount of bandwidth available on the satellite. We hope to be able to do a full chain sync over the satellite soon. That's pretty much the basics here of the satellite process. If you look at the console here, you'll see the amount of block data that we've received so far in the last few minutes since I set this up is 6.52 megahertz, or megabytes, sorry, and no API data at the moment. Now the API data allows anyone to send any arbitrary data via our satellite network, and they can pay for that with Lightning. And we've had a lot of interesting things that have been transmitted over the last several months since we launched the service. Everything from the Brexit documents to some poetry, to we got a new service for those who are in censored areas. Because with this simple setup, which is only about $100 in parts minus the laptop, you can receive blocks and the API data almost anywhere in the world. We have near worldwide coverage. We're around 97% of the Earth's landmass, and the oceans are not yet covered. But I think that is about it.
Okay.
Any questions? Adam, any comments?
So thank you. So that's the kind of setup. There's open source software you install to get to that stage. And positioning the dish is a little bit of an art form, because you've got multiple dimensions. So you've got the elevation, the angle. So they're all geostationary satellites, so they're over the equator. There is a tool on the website where you put in your position in coordinates or addresses or something, and it will give you the angle to point it at in sort of compass bearing, and also the angle to point up in the sky. And the LNB has to be rotated in the right orientation as well. So there are two polarizations, kind of vertical and horizontal polarization, so you may have to switch it 90 degrees to match the polarization. So the instructions about how to, the tool to find the satellite, there are applications you can get for smartphones which sort of give you a loose position of a satellite. So there was some more data that we presented during the panel, which was a few demos ago. So there are actually 4 geostationary satellites that we're leasing bandwidth on. The last one went online quite recently, like a month or so ago, and covers Asia and Australia and New Zealand, the Asia Pacific region, with 2 transponders. So that brings the coverage to closer to global. Now, with the API, you're able to, as Chris mentioned, the main function of the satellite service is to broadcast Bitcoin transactions followed by compact blocks, and to repeat that in case you have power outages. But as we had a small amount of additional bandwidth to requirements for the Bitcoin data, we added an API which you can find on the Blockstream satellite website, where you can put a short text message and pay with Lightning, and it gets put into a queue and sent on the satellite. So it's a kind of small auction. The highest priority messages in terms of fee per byte get sent first. The messages are short so that it doesn't delay transfer. So I think that's the main points we wanted to cover with the satellite. The use cases are actually quite diverse. So it's, the biggest thing about it is it's an infrastructure component. So it fits together with, as in terms of having an internet connection to use Bitcoin, it's an alternative to that. It's the infrastructure component, right? So to get from having a satellite dish and receiving this data in an area with very spotty internet coverage, there are more things you need. So maybe you want to set up a desktop computer, set up a Wi-Fi hotspot. If you look online, there's a demo that Grubel's put together, which includes a Electrum personal server that we saw a demo of from Chris, the other Chris, earlier. And so he was able to run an Electrum personal server that was being fed blocks from the satellite, and set up a Wi-Fi network and connect hardware wallets and a smartphone application to the Electrum personal server. So he was basically able to make hardware wallet secured transactions using smartphones and laptops and Wi-Fi with no internet connection in sight. And then the last hop for how to actually send a transaction, he used the GoTenor equipment that you saw demoed earlier. Now, the GoTenor equipment is a mesh network, so you have to be within mesh network hops of an actual internet connection, but there are fully off-grid internet services you can buy. So separately from this satellite service, there are bidirectional satellite data services. Typically, they're quite expensive per megabyte, but Bitcoin transactions are a few hundred bytes, so the per byte cost is quite low if you can amortize it by sharing the uplink connection between many users, basically. And there's another kind of very mobile internet connection, which is Iridium Go. So the Iridium Go is a type of battery-powered Wi-Fi box that is completely portable and omnidirectional and can send data through the satellite, but it's extremely slow. It's like pre-dial-up speed, so it's 2400 baud for people who were involved in computers very early. That's extremely slow, but it's enough to send a Bitcoin transaction within, a few seconds or something. So using that piece of equipment and a Blockstream satellite and like maybe a Wi-Fi network, you could actually send a transaction from basically anywhere. So that's the kind of infrastructure aspect of it. But we are looking for people with Bitcoin embassies or remote communities and a technical expertise from IT experience to set up interesting configurations and contribute additional configurations such as Grubel's configuration, or optimize smartphone wallets for reduced bandwidth use. You can also couple this with the SMS gateway that was demonstrated to send transactions via SMS if you have SMS coverage. So other than the kind of global coverage and infrastructure aspect, you do have other use cases. So for people with even high-speed bandwidth, it's quite interesting from a privacy perspective because you receive the blocks completely anonymously because it's a passive receive-only technology. So, even if you're just connecting to the peer-to-peer network with a full node and you're using it for security, if you don't use Tor, it reveals your IP address to other peers on the peer-to-peer network. And we know there are people who are trying to analyze the Bitcoin network systematically for taint tracing and other uses. So using the satellite would mean that the people on the network wouldn't see your IP address because you're just receiving it. And then when you go to send a transaction, you can do that over Tor. It's a very small amount of bandwidth, so people won't be able to tell that you're running Bitcoin from the bandwidth profile of your network usage. So that's a kind of privacy and personal security use case. Another interesting use case that we've had actual interest from Bitcoin ecosystem for is mining. So some of the mining farms are in very remote locations. I happen to know firsthand that there's one in rural northern Canada, and I think it's the one that actually had a double internet connection failure, and they had to run the whole mining farm from GPRS data on a cell phone. And if you're operating mining, you can lose a lot of money very quickly if you've got power and you can't mine and you don't have an internet connection. So one of the questions during the panel about off internet use was how could you mine using the satellite? So while a block when it's found is 1 to 2 megabytes, let's say, in practice, you can save a lot of data on that because the first thing is the Bitcoin protocol has compact blocks. So what is actually sent when a block is found is a kind of summary of which transactions that have already been broadcast are in the block plus the missing transactions. So that reduces things by a factor of 10 to 20. But beyond that, it would be quite possible to send block proposals through the satellite to help people that are mining. So a block proposal would be a compact block to say, well, this is a recent collection of the highest fee-paying transactions. We suggest you mine on this. And then the only extra information that's necessary to claim the block when you find it is your address as the miner, where you want to get paid, and when you're mining, your ASICs are counting. So you need to broadcast the counters. But all of this information is, 300-400 bytes, so it's really not very much. You could, send the results of your mining activity in a couple of SMS messages, or in one of these Iridium Go connections, which on the scale of a mining operation is a pretty reasonable cost. So I think those are the most sort of interesting use cases: privacy, global reach, and mining. Also interesting just generally for avoiding network splits. So because Bitcoin is based on a single source of truth, the longest, highest proof of work chain. Now, if you have a network split, so people who are not familiar with ISPs may not know the details of this, but it's more common than people would imagine that the network, the internet continues to function even though parts of it are kind of partly isolated or isolated in one direction and weird things like that. And it will happen because, somebody in an island country like Malta some construction or a fishing boat accidentally snags an undersea cable with an anchor or something like that, and then there will be no internet for half a day while somebody gets the divers to repair it, or they find another temporary internet connection. So with Bitcoin, with the one true ledger, if you had a region that had a reasonable amount of mining equipment that was temporarily network isolated, there's a risk that you could think that you'd accepted transactions, but actually you're on like the wrong part of the network, and the real network is longer. So just a few people within that region with access to the satellite can send that inside their temporary network split and convince people that, no, this is the wrong chain. You're looking at something that's falling behind. So that's pretty interesting for protecting the network from network splits, and just generally providing redundancy and reliability. Now, really, the interesting thing for the global reach is that somebody could basically, without any infrastructure at all, so basically, a hut that's selling, whatever produce in a part of Africa or a desert or something with no infrastructure, just a generator, satellite dish, solar panel, a bit of the equipment that we showed on the roof, and some means to send transactions back, like Iridium Go, or another form of bidirectional internet that's expensive per transaction, but cheap if you're not sending much data, would allow global Bitcoin reach. So that's where we are today, and we're continuing to evolve the technology to improve latency, improve coverage, and add more features to the API and the ways that you can use it. And there's been a fair amount of interest from technical user community to add configurations. And I think when we did the initial launch, this particular SDR type sold out on Amazon. So we don't actually know how many people are using it, which is a kind of a feature, because we can't tell. We don't know who the subscribers are because there are no subscriptions. You just connect your equipment and point it at the satellite, and you're off running. So that's where we are. I'm not sure how we are on time, if there's time. Oh, okay, we can switch back. So Chris, you're back on.
Oh, yes. The one other thing I wanted to mention about this is that the use of Bitcoin fiber, the main purpose for this is due to the forward error correction that fiber provides natively. And that's why we found it perfectly suitable for the satellite application. Since we have a one-way communications channel, you can't really send ACKs back. So the forward error correction ensures reliable delivery of the data when in the absence of that. And then we further, as I mentioned earlier, send the last 144 blocks in case you do miss so much that you can't get caught up with just the error correction data. But I think we're also going to prove that this is real time and we're not faking this up here. So I think I'm going to bring the camera over here a little bit.
So I know that there is some adversarial thinking people down there. I mean, you never trust, you verify. So this is true. The block was 44111ABECAHC. Of course, you may think this is a deep fake video. That's possible. As you read the real, this is happening now. I am my team yesterday, so you have proof.
Thank you. Questions?
We're losing your audio a bit, but I could expand a bit on so one of the things Chris mentioned there is fiber, and that may be something quite technical that people are not familiar with. So in general, Bitcoin transactions and blocks are broadcast through the Bitcoin network, which is sort of peer-to-peer on the internet. So it's not really broadcast, it's just using a lot of bandwidth and sending the data redundantly over many links. And that's done using the Bitcoin protocol, which is implemented in Bitcoin reference implementation and other implementations. But that protocol is traversing many hops across the network. You know, there are up to 100,000 nodes on the network. So if you imagine each node having 8 neighbors on average, you can see that if you take the base 8 logarithm of 100,000, it can be potentially, and it's not uniform, right? So it can potentially be, you know, 10 or more hops. So, and each node is verifying the transaction of block information sometimes before passing it on or partially verifying it. So that verification slows down the transmission as well. So miners have a very strong financial interest to learn about new blocks very, very quickly and with very low latency. Because if if you're mining and you're mining on the wrong block or on the old block for 10 seconds every 10 minutes, that's actually pretty expensive. That will cost you some percentage of your revenue, and that's revenue, right? There's the profit margin because the input costs are quite high. So there's a kind of arms race to get very low latency notification of blocks within the Bitcoin network. And so at some point a few years ago, Matt Corallo implemented a protocol to improve this called Fiber. And what it does is, you know, basically one of the bottlenecks with the Bitcoin network is, firstly, it's peer-to-peer. The network connections involved are random, so you know the traffic may be crisscrossing the globe backwards and forwards. It's not locality aware. So Fiber is a bit more of a curated peer-to-peer network. So people who are interested in achieving low latency will, you know, add themselves to the Fiber network. They'll figure out where they fit in geographically, and they've rented, you know, computers in interesting strategic places with low latency between different continents and countries to try and build, you know, hand-curated, very low latency transfer path. So that's the kind of network topology optimized, and then the protocol itself is also optimized. So with TCP, which Bitcoin uses, you send data and the remote computer says, oh, I got that, and then you send the next piece of data. So there's a kind of flow control protocol. And just due to speed of light, you can see, you know, 100 millisecond ping times, things like that. So if you've got a three-way to and fro, that actually slows things down. So what Fiber does is it uses forward error corrections. So it doesn't wait for responses. It just sends data, and it sends more data, so that if some of it's lost, it can reconstruct the missing data from the redundancy. So that's the forward error correction that Chris was using. And the same kind of technology is used in broadcast, in mobile phone codecs, and in CD-ROMs. So basically, it's able to reconstruct missing data. So there's a quite high degree of redundancy in what goes over the satellite. So there's 3 times redundancy in the kind of top-level codec, and there's another 30% redundancy in the other forward error correction. So it's a very interesting bit of technology, and it's, you know, sometimes people will say, well, we can push Bitcoin harder, just, you know, increase all the parameters. But actually, Fiber is showing that the Fiber network is very close to the speed of light for transferring blocks, and the speed of electricity in a wire is like slower than the speed of light, about 2/3 of the speed of light. So the amount of milliseconds it takes for a block from a miner that's found it to go everywhere else is actually pretty impressive these days, and that won't really improve because the speed of light is a constant as far as we know. So that's one of the kind of trade-offs in Bitcoin. Anyway, so I just wanted to explain what people were talking about when they were talking about Fiber. So I guess it's probably time to wrap up and take questions.
Yeah, we can probably take a question or two because that was a lot. So we can take a question or two on this, and then we'll just do closing statements. All right, go ahead.
Adam, you mentioned an anchor ripping up the undersea cable, and then you have kind of a network partition. And just to verify that the blocks that are currently in Malta, for instance, are the right ones, wouldn't it take a lot of hashing power inside Malta to even generate a new block?
Right, so you would be protected by the disparity in hash rate. Now, it would be more worrying if, let's say, China were to get partitioned, either due to physical disruption or political disruption, because they have so much hash rate at times, I mean, it varies over time, that you could get partition. And the other thing to bear in mind is that, you know, people think of network partition as a binary, like the link is down or up, but you get, you know, when you do network programming and network protocol design, you have to consider very strange network conditions where routers have been misconfigured by accident and things like that. So sometimes you get a situation where you can receive the data, but you can't send the data, or you can see one person that's outside, but not the other. So the networks can be unpredictable, so you really want to have redundancy in your network connection. I think for people who don't have, you know, let's say for a Bitcoin exchange or something with high value, payment processor, a merchant, they would ideally have, and particularly for miners, they would ideally have multiple network connections. So they might have a normal network connection, they might use 3G data device or some other network connection, and keep some of them private, because, you know, for a miner or a pool, it's quite expensive if you get DDoS or somebody manages to compromise the network or your network connection, or trick your service provider into disconnecting your network service or something like that. So some of those things have actually happened because there's big money at stake, and you know, not everybody's practicing fair play. It's when there's money at stake.
All right, we got 2 more questions. Max, World Crypto Network.
Well, thank you very much, Adam, for doing this. It's cypherpunk as fuck, so lovely. A question for sending Bitcoin transactions to the satellite. Would there be a possibility of de-anonymizing the location from where the transaction is being sent, or how anonymized is that?
Yeah, so, I mean, it is possible to triangulate satellite transmitters. They are transmitters, but it's, you know, if you just fire one off and it's not persistent, I think they don't really have the technology generally to triangulate that quickly. And you can use mobile equipment as well. So, but it's, you know, the data coming down from the satellite is anonymous because it's covering the same data everywhere. Now, I mean, technically it can provide a different fiber stream to different satellites. So in some areas you have visibility of 2 satellites. And so if you set up 2 satellite dishes, so the Bitcoin Satellite project was originally something discussed by Chris, who's been demonstrating from the roof, and Gregory Maxwell, who is a well-known Bitcoin developer and used to be, working for Blockstream. And so he has been, you know, working on this project in his spare time, and has set up 2 satellite dishes, because his area where he lives in the US can see 2 satellites. So he's able to receive 2 streams. And in principle, when we switch it over to having 2 different forward error correction streams, he would actually be able to get the data with half the latency because of this. So the forward error correction is kind of interesting, magical network technology that you can, you know, people can beam parts at you, and as soon as you get enough parts, any parts, you can reconstruct the data. But yeah, as soon as you're broadcasting with radio, you become triangulatable, but I would say much more so if you're stationary and if you keep doing it and sending a lot of data. Now, a Bitcoin transaction is kind of a pop up and fire a few hundred bytes for a second and disappear with the mobile equipment, so I think that would be less of a concern.
We got one last question.
Hello. Thanks for the talk. I was wondering about the fiber and the forward error correction. Does that survive things like electrical storms, solar storms, cloudy weather, or that kind of thing? Are you aware of bad weather affecting it?
Yeah, it does tend to. I mean, so the satellite coverage is not completely uniform. So there are regions which are, you know, further by line of sight, so they're closer to the horizon, and we try to do the tuning so that you can receive the information even with a 45 centimeter dish, which is the smallest typical satellite dish, but still with some margin for error. So we could actually send a lot more data if we were gung-ho about, you know, people with rain at the edge not being able to receive it. So it's supposed to be tuned so that it should work, but There's also error correction within short time frames. So, you know, if you had it set up on a patio and somebody walked in front of it, you know, for a second, you wouldn't lose the data stream, basically. So there's a short kind of interruption recovery, and then there's the longer range recovery if you have a power cut.
All right, thank you very much. All right, thank you for the awesome presentation.